Welcome to the Chemistry YouTube channel. Today what we are going to see is Maharashtra SET exam 2020 question with a detailed explanatory answer, paper 2, chemical science. Question number 1. The bond angle of the tetrachloride for the following group 4 element is following in the order. Group 4 element, that is carbon, silicon and germanium has been given. So what happens as we move down the group? Each of these compounds has the formula of XCl4. They are simple covalent molecules with the typical tetrahedral shape. We know that all these SiCl4, CCl4 and GeCl4 has tetrahedral shape, but the covalent character, the covalent bond, decrease with strength in increase in atomic size. Listen, as the atomic size increases from carbon to germanium, the covalent character increases. Hence, the ionization energy of the heavier element also increases because of higher effective nuclear charge. The ability to form pi-pi multiple bond among themselves decreases down the group. This you have to remember. So on increasing atomic size, covalent character increases. Hence, option C is correct. GeCl4 has more bond length than silicon SiCl4 than CCl4. CCl4 having a less bond length, whereas bond length is inversely proportional to bond angle. It's inversely proportional to bond angle, whereas in case of bond angle, CCl4 is greater than SiCl4, greater than GeCl4 and SnCl4. Because BAB bond angle decrease with decrease of electronegativity. Question number 2. In the reaction, water reacts with Cl minus is an anion to give anionic complex. Water reacts with a cation Mg2 plus to give a cationic complex. So here what will be the option? Water acts as an acid in both 1 and 2. Acid in 1, base in 2. Base in 1, acid in 2. Both base in 1 and 2. Here, water can act as both acid and base. Hence, option C and D are ruled out. Undergo autoionization. H2O gives H plus OH minus. Water can act as a reducing agent because in reaction Cl2 is converted to HCl and liberates oxygen. Here the oxygen is liberated in 1. Water acts as an oxidizing agent and liberates hydrogen in 2. Here hydrogen is liberated. Hence option B is correct. Acts as an acid in 1 and base in 2. Question number 3. Carbon monoxide CO is isoelectronic with which of the compound? Isoelectronic species are those species which have the same number of electrons. The ion that is isoelectronic with the CO, carbon monoxide, is N2 and Cn minus. Here CO has 6 plus 8, carbon 6, oxygen 8, 14 electrons. In Cn minus, carbon 6, nitrogen 7 and one minus, that one minus has 1 electron. So total 14 electrons. In nitrogen it's 7 plus 7, 14 electron. Hence, isoelectronic species is A and D. Both are correct. Which of the following statement regarding solubility of lithium fluoride and lithium iodide in water at room temperature is correct? Option A, both are equally soluble. Both are insoluble. Lithium fluoride is more soluble than lithium iodide. Lithium iodide is more soluble than lithium fluoride. Here, the answer is the lithium fluoride is more soluble in water. Because according to Fajan's rule, you take Fajan's rule, fluoride ion, F ion, is smaller in size and the iodine ion is larger in size. This lithium, being smaller as compared to iodine, fluoride will be more polarized to a greater extent. Hence, lithium fluoride is less covalent. Lithium fluoride is less covalent as compared to lithium iodide. Hence, lithium fluoride will be more soluble in water as compared to LiI. Here, lithium fluoride is more ionic and lithium iodide is more covalent. Hence, option C is correct. Lithium fluoride is more soluble than lithium iodide in water. You have to apply Fajan's rule. Question number 5. Hydrogen bond strength in OH. This hydrogen bonding is in intermolecular hydrogen bonding. Which hydrogen bonding is more stronger? The strength of hydrogen bond decrease in the following order: HCl greater than O greater than N. Smaller the size of electronegative atom, greater is the attraction of bonded electron pair. This causes a greater polarity in the hydrogen and electronegative atom, resulting in strong hydrogen bonding. The size of, listen, the size of chlorine, oxygen and nitrogen is in the following order: chlorine less than oxygen less than nitrogen. Hence, here option B is correct. Second one is a chlorine greater in size than oxygen, which is greater in size than nitrogen. Hence, option B is correct. The type of hybridization in diamagnetic NiCN4 2- and the paramagnetic complex NiCl4 2-. What is the hybridization you have to detect? In NiCl4 is a paramagnetic complex, is a Ni2+ oxidation state, it's a D8 configuration. Hybridization involved is sp3. Here Ni2+, so it's a D8 complex. One s orbital and 3 p orbital hybridized to give sp3 hybridization. Whereas you take in NiCN4 having a very strong ligand, Here Cl4 is a weak ligand and CN4 is a strong ligand. All the ligands will be get paired. Ni2 plus 1, 2, 3, 4, 5, 6, 7, 8. And is a d orbital s, and hybridization will be dsp2. Hybridization is dsp2. So answer is in CN4 for strong ligand hybridization is dsp2, and for weak ligand Cl4 hybridization is sp3. Answer B is correct. Question number 7. The IUPAC nomenclature of the complex. A complex has been given. First we calculate the oxidation number. For platinum it's X, bromine it's a -1, ammonia is 0, for chlorine is -1, and NH2CH3 is 0. So total oxidation number is X equal to +2. Hence in this 4 option platinum oxidation is given +2. Okay. Next you have to arrange the ligand according to the alphabetical order. In alphabetical order arrangement of the ligand, the D is correct. Amine, bromido, chlorido, methylamine, platinum 2. Hence option D is the correct answer. Question number 8. The number of EPR lines observed in Cu, pyridine 2, Cl2 will be given. The nuclear spin of copper is 3/2. EPR line, there are two different splitting. One is the splitting by copper and another is the splitting by pyridine and chlorine. Here you write 2Ni plus 1 into 2Mi plus 1 lines. For metal atom copper, N is 1, so 1 copper, and I is 3/2. For ligand pyridine, there are 2 pyridine, there are 2 chlorine atom, so totally 4 atom, and I equal to 1/2. So 2Ni plus 1, that is 2 into 1 into 3/2 for copper. This is for splitting by copper. 2 into 4 into 1/2. This is a splitting by ligand. So it's 4 into 5, 20 lines. So this is a structure of this complex: copper, 2 chlorine ligand and 2 pyridine ligand. The splitting gives 20 lines. Option A is correct. Question number 9. A polycrystalline powder X-band EPR spectrum of a 6-coordinated copper complex exhibits G11 2.35 and G1 2.06. The G value has been given. The nature of this spectrum will be to determine the intermediate radical trap, that is a DMPO 55 dimethyl 1 pyrroline N oxide was added. In this 1:1 complex, the intermediate of DMPO was isolated, and the EPR spectra of this copper compounds indicates the elongated axial bond with the intermediate. So this is the intermediate compound of, here you see is a elongated axial bond. Hence option C is correct. Question number 10. The touching frequency of free carbonyl CO, Cn minus and NO nitrosyl in IR spectrum will be. Here for cyanide Cn it is 2250 centimeter. CO free carbonyl group it is around 1700 to 1750, and for nitrosyl NO is around 1500 to 1600 centimeter inverse. Hence Option A is correct. Cn minus greater than CO greater than NO. Question number 11. The only electronic transition that occurs in copper tetrahedral complex is. You take a copper tetrahedral complex Cu NH3 2 plus. Here this copper Cu2 plus shows D9 configuration. With one unpaired electron. For this, the ground the term symbol is D2. So the splitting gives this D2 splitting gives T2 to E2. T2 to E. Here it is term is 2, hence we will put the multiplicity 2. So the electronic absorption band occurs from T2 to E2. Here it's option B is correct. T2 to E2. If the electronic transition occurs from T2G to EG means it is in octahedral complex. Listen, if the complex is octahedral means here the absorption will be gives absorption T2G to EG. In tetrahedral complex, they are asking for tetrahedral complex. Then tetrahedral complex from D1 to D9, you should not mention that the term G. The term G will not come. This G will not come. This G will not come. Only absorption from T2 to E2. Option B is correct for tetrahedral complex. Option A is correct for octahedral complex. Question number 12. The correct order of magnetic moment of lanthanide ion, lanthanum, gadolinium and cerium. You have to see the magnetic moment, the unpaired electron. You see in lanthanum, for lanthanum it's a 4f0 having unpaired electron 0. It's a colorless compound with magnetic moment is 0. For cerium it is 4f1 where the unpaired electron is 1. It is also colorless with magnetic moment 2.54. And they are asking for gadolinium. For gadolinium is 4f7 having 7 unpaired electron. Hence it's half filled, so it is also an colorless, having magnetic moment, a maximum magnetic moment that is 7.94. So this is the order. Option B is correct. Gadolinium having 7.94 magnetic moment greater than cerium, it is 2.54. Whereas for lanthanum the magnetic moment is 0. It is a diamagnetic. Question number 13. The first absorption level for VF63 minus complex is observed to be 14,800. The 10 dq value for the complex is a V3 plus, vanadium 3 plus having D2 configuration. Here the absorption band is 14,800. It's for 8 dq. For 10 dq, delta is 14,800 divided by 0.8. It is 18,500 centimeter. 18,500 centimeter inverse. Question number 14. The geometry of NSiH3 silicon trihydride will be tetrahedral, trigonal pyramidal, trigonal planar and linear. Here the linear will not come, and tetrahedral also will not come because tetrahedral shape is shown by ammonia. So here we will see in case of NCH3 geometry pyramidal, in case NSIH3 geometry is planar. In trimethylamine, nitrogen atom is sp3 hybridized because it contains a lone pair electron, which results in a pyramidal geometry. There is no pi bonding because no d orbital. CH3 it has a lone pair electron, it has no d orbital, so it is a pyramidal structure. Whereas in trisilylamine, nitrogen atom is sp2 hybridized, which results in a planar geometry. There is a pi d pi bonding because silicon has a vacant d orbital. Filled 2p orbital of nitrogen overlap with vacant d orbital of silicon. Here you see, in this here the nitrogen is sp2 hybridized in NSIH3 thrice. Here this silicon donates a pair of electron to empty d orbital of nitrogen. So this is having a planar geometry. It's not pyramidal or it's not a tetrahedral, it's a planar. Having a planar geometry, it's a trigonal planar. Whereas in NCH3 thrice, it has lone pair electron. It is a sp3 hybridized with a localized lone pair to produce pyramidal geometry. Here a back bonding occurs. The electron density of nitrogen in delocalized result in electron density, that is the electron is donated from nitrogen. This nitrogen donates the lone pair of electron to silicon. Empty d orbital, 3d orbital of silicon is a pi d pi back bonding. Trigonal planar. Option C is correct. Tetrahedral shape for ammonia, trigonal pyramidal shape for NCH3 thrice, and trigonal planar for NSIH3 thrice. Question number 15. The driving force for the complexation of magnesium 2 plus by EDTA in aqueous medium is change in oxidation state of magnesium, increase in entropy, change in coordination geometry, decrease in entropy. The change in oxidation state of magnesium of certain atom in ligand donate one free electron pair to the central metal ion. Change in oxidation state increase the change in entropy of the reaction. Hence, option B is correct. The increase in entropy is the driving force of complexation of magnesium EDTA. Thank you for watching. We will meet in the next part 2 video. Thank you.